Hi, George Diamond here again, and welcome to my flipped classroom. We're learning a little calculus today, and what we're looking at today, we're going in our textbook. This is section 7.2. We're going to be calculating volume. Now today we're looking at a technique called the disc and washer method. Now in video number 1, we're going to be focusing on just the disc method. In video number 2, we're going to look at the washer method. So if you want to see some examples of calculating volume using the washer method, then check out my second video. We're going to look at about 5 examples here. But first, a little bit of information. I said we'll be looking at calculating volumes of shapes that have been rotated about a line, right? And that's what a solid of revolution is. A solid of revolution is simply a region in the plane, okay, revolved about a line called the axis of revolution. So when you revolve something about a line, okay, you get a solid, what's called a solid of revolution. So if you can imagine a lot of things in industry, things that are circular, and I've got a container of Kool-Aid here, so I don't know if you can see it, but you can imagine if you could describe the outline of this Kool-Aid, okay, with a shape, with a formula of some type. And if you can imagine a straight line passing down through the center of this Kool-Aid, you know, if you could rotate that equation or that formula that will describe the outline of this shape, if you can rotate this about a line, if you will, you get this type of shape. Circular items. In an industry, you know, I'm sure this type of thing is done every day, where they have to maybe describe an outline or a shape with an equation of some type. So, now what happens in what we're going to be looking at here with the disc and washer method, it starts off with an axis of revolution. So if you can imagine, I don't know if you can see it here, hopefully you can see it on my marker board here. You can see that little rectangle drawn. But it starts off with what's called the representative rectangle. So this involves creating a disc. So if we take this rectangle, which is perpendicular to the axis of revolution, and we rotate it 360 degrees around that line, okay, we get a disc. Right? So we rotate that about that line, we get a disc. Now a disc is simply a right circular cylinder, or a flat, somewhat flat right circular cylinder. But as you look at the volume of a disc, so as you look at this rectangle, okay, you got your width. This here is going to be your width. This here would be the length. Now, whenever we rotate that rectangle about the axis of revolution, the length of this rectangle will also be the radius of the disc. Right? So it's going to be the radius of that disc. So when you think of the volume of this disc that's created, right? So maybe a flat right circular cylinder, the volume of that disc is going to be pi times its radius squared times its width. Right? So pi times a big R squared times W times its width. Now to move this along, let's describe how this is going to apply to the volume of a solid that's revolved around a line. Right? Start off with volume of a region rotated about the x-axis. Now you can see this region here that I've got graphed. You can see the region in red, and the region below the curve. You can see my representative rectangle drawn here. Okay, now the radius of the representative rectangle is Rx. I'm going to let Dx be a real thin width, if you will. Now what happens in calculus, you know, as you can imagine from left to right, when this is being rotated about the line, you can imagine this representative rectangle from left to right. The width, the height of the rectangle will be the radius of the disc is going to change from left to right. And this is where the integral, the derivatives comes in as we set up our integral. Okay, it's based upon the volume formula for a disc, pi times the radius squared times the width. So to get the volume of this region, it's rotated about the x-axis. Now the region that I have drawn here, if you were to rotate this about the x-axis, you would get a bowl shape. It would be sideways like that, but you would get a bowl shape if you can imagine rotating this. But the formula we're going to use, if it's rotated about the x-axis, is pi times the radius squared. So in this case, from the upper bound to the lower bound, from A to B, A will be our lower bound on our integral, B will be the upper bound. Times the radius squared, so the radius of that disc squared. Now the radius of the disc is going to be where the disc touches the y value, if you will, of your of your curve. So it's going to be your function squared, basically, times dx. dx is going to be the width of that disk. All right, so it's pi times the integral from a to b times rx times dx. Now, if we're rotating that shape about the y-axis, all right, so this time we have, this time you can see our y-axis. This time I'm going to draw my representative rectangle so that it's, once again, perpendicular to the y-axis. Now this time we're rotating our disk this direction, all right? So you rotate this. This time we end up with a bowl that's kind of upside down, so you can kind of visualize this. I didn't even try to draw it. And it's, they're difficult to draw in 3 dimensions. But this time, you have to solve this for x in terms of y, all right? And our lower bound would be c, or upper bound would be d. Okay, r sub y would be the radius of our disk, all right? dy this time would be a small increment in y. That would be that's going to be the width of our disk. So our volume formula we're going to use is pi and times the integral from c to d times r sub y squared times dy. Now, if you can imagine, if you were to rotate this shape right here about the x-axis, you would get something like this. You get some type of a bowl shape. Right? So same thing here. You would get some type of a bowl shape if you were to rotate this. It would look sort of like that. So an upside down bowl. Right? So like I said, these are kind of hard to draw, just freehand drawing them on the board. Now I've got some I've sketched, but the 3-dimensional aspect is just really difficult to draw. Okay, now this is a little information here as we get started. Once again, rotating the region about the x-axis is pi times the integral from a to b, right, r sub x squared dx. So let's get on with our first example. Right? We got about 5 examples we're going to run through. So let me get this erased, and let's take a look at our first example now. Rotating a region about either the x-axis or the y-axis. So let me erase this. There we go. Okay, let's pull up our first problem here. I already got this sketched out, so let me take a look at it here. Okay, problem number 1. Now see if we can find the volume of the region bounded by the graphs of y equals the square root of x, the x-axis, and the line x equal 4 about the x-axis. So we're going to rotate this about the x-axis. So when I draw my representative rectangle, you can see this is the graph of the square root of x. Okay, this is the line x equal 4 is a vertical line, right? And you can see this region right in here. So we're going to rotate this about the x-axis. So, and as we get started, let's set up our integrals. We set up our integral here. This would be, so problem number 1. Our volume is going to equal pi, the integral. Now we're integrating from 0 to 4. All right, so the lower bound will be 0, the upper bound is going to be 4. All right, now as we rotate this about the x-axis here, the radius would be the square root of x squared dx. So once again, as you set your integral up, think of the volume formula for a right circular cylinder. Okay, pi times the radius squared times the height. Where dx would be you imagine dx as being the height. So just have to remember pi times the radius squared times the height. If you can remember the volume formula for a cylinder, you set up your integral pretty much along that same line. So let's see what we get when we let's see what our volume would be as we evaluate this integral here. Now first I want to simplify it a little bit. So this would be pi times the integral from 0 to 4. Now the square root of x squared is just x. So you get x dx. Now this is going to be simple. The antiderivative of x is x squared, so we have pi times x squared over 2 from 0 to 4. And believe it or not, one of the most common mistakes that students make with these solids of revolution where they have pi is I like to pull the pi out in front of my integral. Now you don't have to. You can leave it inside the integral as pi x. You can still get the same answer, but a lot of times I like to pull pi out in front of the integral. But you've got to be very careful that you don't forget about pi. Right? You got to, at the end of the problem, we're going to find our antiderivative, and at the end we got to remember to keep bringing this pi down and multiply pi at the end of the problem. Okay, we got our antiderivative, so we're just using the power rule. You got an exponent of 1, so you're going to add 1 to your exponent divided by the exponent plus 1. And this will give us pi. And I'll substitute the upper bound minus the lower bound now. This will be pi times 1/2 times 4 squared. Okay, minus. substituting 0 in for x gives us 0. All right, and 4 squared is 16, half of 16 is 8, and the volume is 8 pi. So that would be our volume. And a pretty easy example here for problem number 1. All right, let's try another one. So we'll start off with a fairly simple problem. Let's try number 2. So erase this. Now, let's try a trig function. All right, let's try this one here. Number 2. And, well, yeah, I just came from a soccer game just a little while ago, so fairly exciting. So let me get rid of this soccer ball, let me get it out of the way. It's kind of unusual. So now let's take a look at problem number 2. And let's see, now this time, let me find it here in my notes. Here we go. Right. Now problem number 2 says find the, so what was the volume bounded by the graph of f of x equals the square root of sine x and the x-axis. It's rotated about the x-axis. So as you look at the region, now if you graph f of x equals sine x, this is what the graph would look like. These are kind of repeated, so we're just, once again, we're restricting our volume here from 0 to pi. So as we set up, now you can see the lower bound here would be 0. Okay, the upper bound is pi, so as we set up our integral then, our volume, number 2 here, we'll describe our volume as pi times the integral from 0 to pi, the square root of sine x squared dx. Right, so once again, remember as you set your integral up, remember the volume formula for a right circular cylinder, pi times the radius squared times the height. So pi times, imagine this is your radius squared times the height. Now let's simplify the integral first, and then we'll find our antiderivative. This will be pi, integral 0 to pi. The square root of sine squared is just sine, so it'll be sine x dx. Find our antiderivative, this will be pi times negative cosine. Antiderivative sign is negative cosine x from 0 to pi. And let's see, I'm going to pull the negative out front here. So it'll be negative pi. All right, it'll be a little bit easier. Cosine, okay, x from 0 to pi. And substituting pi in for x, we have negative pi. So negative pi times cosine pi minus cosine 0. All right. Now, cosine pi, remember the unit circle. Pi is here, and that's at negative 1, 0. Okay, the x value is cosine, the y value is sine. So sine is, cosine is x, sine is y. So cosine pi would be negative 1, so we have negative pi. Cosine pi is negative 1 minus, now cosine 0. So cosine 0 would be here, so 0 here, let's be the point 1, 0. So 0 degrees. Point 1, 0, so once again cosine here would be 1, so it would be minus 1. Now let's see, 1 minus 1 is negative 2, so we have negative pi times negative 2, or 2 pi. Again, the volume of this region, were it revolved about the x-axis, you would basically get something like a ball, you know, like a baseball or something like that. So it would be very round, so very round. So it would be 2 pi would be our volume. And that would be 2 pi units. Units cubed. So units cubed. All right. Let's look at example number 3. So moving right along. It says we have 5 examples altogether we're going to look at. So let's take a look at our next one. There we go. Let me get this one erased. Okay, let's try this problem right here. So problem number 3. Find the volume of the solid found by revolving the graph of y equals 4 minus x squared, a little parabola. X equals 0. Now x equals 0 is simply the y-axis. The line y equals 0, which is the x-axis, about the x-axis. All right. So if you look at this, region, you got x equals 0. That would be the y-axis. And you have y equals 0. That would be the x-axis. We're going to take this region and we're going to revolve this about the x-axis. So let's see what we get. How are we going to set this one up? So we'll look at our graph, and let's see. We've got our volume. So number 3. So our volume is going to be pi times the integral. Now once again, this time we're going to integrate from 0 to 2. So 0 will be our lower bound. 2 is going to be our upper bound. And this would be 4 minus x squared squared dx. Okay, so let's see now. But to begin with, we're going to have to simplify our integral a little bit. So let's just go ahead and square this binomial. This will be 4 minus x squared times 4 minus x squared. Now I'm just going to FOIL it out. All right. This will give us 16 minus 4x squared minus 4x squared plus x to the fourth becomes 16 minus 8x squared plus x to the fourth. All right. So to describe our volume now, this will be pi. You got to remember the pi. So pi integral 0 to 2. This will be x to the fourth minus 8x squared plus 16 dx. And this will be, we've already squared it, so that's taken care of. Right. And we're ready to find our antiderivative. So let's get our antiderivative here. So our volume will be equal to pi. Now the antiderivative of x to the fourth is x to the fifth power over 5 minus 8 times x cubed over 3, okay, plus 16x. And this will be from 0 to 2. Now my little problem here, I'm going to leave this up for as long as I can, so if you're taking notes, you may want to make sure you have this written down because I may have to take it off in a minute. I'm not for sure. Some of these problems can get kind of long, so if I need some extra board space, I may have to take that off. So let's see what we get now. We got our antiderivative. Simplifying this a little bit gives us v equals pi. It's be 1/5 x to the fifth minus 8/3 x cubed, okay, plus 16x from 0 to 2. Okay. Now we're ready to evaluate our upper bound minus our lower bound now. So this will be pi times, substituting the upper bound in first will give us 1/5 2 to the fifth power minus 8/3 2 to the third power plus 16 times 2 minus, substituting 0 in for x, this is all going to be 0 here. All right, so that'll all be 0. And let's see, we'll end up with pi times 2 to the fifth power is 32, so it'll be 32 over 5 minus, this will be 8 times 8 would be 64 over 3 plus 32. Right, now to move things along a little bit, we'll end up with 256 over 15, so 256 pi divided by 15. So we'll go ahead and do the subtraction and the addition and then bring the pi in. So this will be our final answer in terms of pi, 256 pi over 15. That will be our final volume. So let's try number 4. All right, number 4. Okay, we'll do one more revolution about the x-axis. I'm going to finish up with a revolution about the y-axis also. So let me erase this. All right. Okay, let's try an e function. So I'm not doing one of those yet. This is a pretty easy one, but let's take a look at it. Right. So what's the volume when revolved about the x-axis? So we'll do another one about the x-axis. This is y equals e to the x over 2, x equals 0, and x equals 4. Right. Now x equals 4 or x equals 0, that's another name for our y-axis. So it's going to be one bound. Okay, x equals 4. So as we set up our integral now, once again, we're revolving this about the x-axis. So once again, when we draw or represented a rectangle, remember you always draw it perpendicular to your axis of revolution. So with the disk method, so as you revolve that rectangle and you rotate that rectangle about the x-axis, okay, you're going to get what's basically maybe a horn shape, some type of a horn shape, I guess, that you can imagine what this would look like. I guess, you know, if you were to rotate this about, you get some type of a horn shape. It looks like that. They're kind of hard to draw. Like I said, it's hard to draw in 3 dimensions, but you know, I'm not much of an artist. That's pretty close there. All right, so we set up our integral. Our volume then will be pi times the integral. That would be integrating from 0 to 4, looks like. So from 0 to 4, okay, e to the x over 2 squared dx. And let's start off. First thing we want to do is simplify our integrand here. So e to the x squared over 2. As we simplify here, we go pi from 0 to 4. Now, I've got to multiply your powers here. This becomes e to the x dx. All right, so it makes it nice and simple. We don't even have to use substitution. The antiderivative of e to the x is itself. All right, so the antiderivative here would be pi times e to the x from 0 to 4. So the antiderivative of e to the x is itself. Substitute the upper bound minus the lower bound now becomes pi times e to the 4th power. So e to the 4th power minus e to the 0 power. So the upper bound minus the lower bound. So now we've got pi from e to the 4th minus 1. Now if you've got a calculator, you can punch it up on your calculator. You can see what the approximated value would be, but this would be the exact value. You know, if this were a problem on the AP Calculus exam, it would probably be a non-calculator problem. You know, so your answer would look something like this right here. All right, let's try one more example. Okay, let's try a revolution about the y-axis now. Okay, let's try a revolution about the y-axis. That wasn't too bad. Go ahead and set this up so we can take a look at it. Okay, so what about the volume when revolved about the y-axis? So you can see we got another little parabola here, a little quadratic. Okay, so we have y equals 9 minus x squared, y equals 0, x equals 0, and the line x equals 3. All right, now the line x equals 3 would be this line right here. Right, so x equals 3. All right, so we're going to revolve this region here about the y-axis. So this time we're going to draw our axis, our representative rectangle has to be perpendicular to our axis of revolution. So we're going to draw our representative rectangle will be horizontal this time. And once again, it'll be perpendicular with the y-axis. So now, the first thing we need to do, we're going to revolve this about the y-axis. The first thing we need to do, our function here, y equals 9 minus x squared, we're going to have to rewrite this and solve it for x in terms of y. Right? So if we were rotating about the x-axis, we would be good to go. We're ready to use our function, but we have to solve this for x. So we're going to solve for x. And we have y equals 9 minus x squared. This becomes y minus 9 equals negative x squared. Change the signs. It becomes 9 minus y equals positive x squared. You take the square root of both sides, be plus or minus equals x. Now notice now, this time plus or minus, okay, this is all positive, so we don't need the negative. This would just be positive square root of 9 minus y. Alright, so square root of 9 minus y. Okay, and as you can see here, we're integrating from 0 to 9 for our upper and lower bounds. So we set up for our volume here on problem number 5. Our volume is going to be pi integral 0 to 9 about the y-axis. Now, remember, we're rotating this about the y-axis. So you got to solve for x in terms of y. This will be y here, not x. In terms of y. And our radical, we will 9 minus y squared dy. Now, so everything in terms of y. So to get started, to begin with, let's see if we can simplify our integrand. Our volume then becomes pi integral 0 to 9 minus y times dy. So remember, when you square your square root, the square and the square root cancel out. That just gives us 9 minus y now. So this will be that should be pretty simple to do. Find our antiderivative. This will be pi times 9y minus, the antiderivative of y is y squared over 2 from 0 to 9. Now let's substitute the upper bound minus the lower bound. Let's see what we get here. This will be pi from, this will be 9 times 9 minus 1/2 times 9 squared minus, substituting 0 in for y gives us 0. So that makes it pretty easy. And what do we end up with now? We have pi times 81 minus, this would be 81 over 2, okay, which would be, let's see, 162 over 2 minus 81 would be times 81 over 2, which would become 81 pi over 2. And that should be our volume to our last problem. So 81 pi divided by 2, Okay, that will be our volume. So this is the, we'll do at least one example where we're rotating about the y-axis. Just remember, when you're rotating about the y-axis, you're going to draw your representative rectangle perpendicular to the y-axis, and it'll be horizontal here. So, so hopefully you found these 5 examples helpful as far as this method. Now, look at my next video. We'll do several examples of the washer method, where it's a little bit more complicated. So you've got a washer is basically a disc with a hole in it, so it makes it a little bit more complicated. And we'll do our next video here in a few minutes.